What range can we achieve with the local LoRa network in real-life situations? Can antennas make a difference? We will look at different indoor and outdoor scenarios, and we will evaluate and predict our LoRa radio channel. Now that we have covered the complete hardware and software of our little project, we go ahead with some experiments. As you can see, we ticked a lot of topics already in earlier episodes. The red monsters are indicating the interfaces that are on the agenda today. For the ones who didn't join the previous episodes, here is the hardware that we use for the coming experiments. Some past episodes covered already the build of the entities and a number of other interesting experiments with battery runtime and solar powering. In today's experiments, the radio channel is mainly our interest. Please note that the two LoRa transmitters are using different antennas. The one on the left side uses a small rubber-coated antenna inside the case. Of course, this is reducing the antenna's performance. We estimate that it is losing about 10 dB compared to a proper external quarter-wave antenna. The transmitter on the right side has an SMA antenna connector so that we can use different external antennas. The agenda for our experiments. We want to measure the RSSI, which is an equivalent of the received power and the field strength. In addition, we will record the SNR, which is the signal to noise ratio of our LoRa channel. There will be two scenarios for two transmitting sensor units. This means we will look at 4 different radio paths to evaluate. Then we will use 5 different antenna types on the receiver side. We want to evaluate and compare the suitability. Considering the various antennas, we will measure 20 different sub-scenarios in total. For the evaluation of our LoRa channel, we compute the median values and the standard deviation for the received signals within a 30 minutes time frame. Then we will compare the RSSI versus the SNR and the corresponding variations for our different antennas. The final goodie will be that we will compare the measurement results with our wave propagation prediction tool. In our scenario 1, we receive the signals in my home office. As said, we use 2 sensors at the same time that are transmitting data via LoRa. Transmitter 1 is in a garage, which is separate from the house. The transmitter 2 is located on the balcony of our flat. Transmitter 1 is in 54 meters distance from the receiver. The signal needs to propagate through 2 walls, the one from the garage and the outer wall from the house. In between there are some trees, which are also adding a considerable attenuation to the signal. Transmitter 2 is in 12 meters distance. And in this scenario, the signal needs to propagate through 2 walls within the house. In scenario 2, we move the receiver to the living room. Transmitter 1 is now in 60 meters distance, and we get an additional loss now from 4 walls and some trees. Transmitter 2 is again in 12 meters distance. However, here we need to take into account the attenuation from only one wall and a thick glass window. For our LoRa receiver, we can choose different antenna types. We have a rubber-coated helix antenna, a self-made broadband cone antenna, an experimental self-made magnetic antenna, and a set of self-made monopole antennas. From the monopoles we choose the one with a quarter wavelength for 866 MHz and a longer one having about double the size. Next, let's have a look on our measurements results that we recorded on a spreadsheet. I will explain the method of evaluation in one case so that you get the idea, and then we will carry on with the same procedure for the 2 transmitters and the 2 scenarios and for the 5 antennas. We recorded here the RSSI level of transmitter number 1 in dBm for each of the received data packets within 30 minutes. From our series of measurements, we compute then the median value and the standard deviation here. We also recorded the SNR level for each LoRa data packet. And we also compute the median and the standard deviation from the SNR. Then we carry out the same procedure for the recorded receptions from transmitter number 2. Then we have to repeat this for all the 5 antennas. Having finished scenario 1, you guessed it, we repeat the same procedures for scenario 2. But what is the point now? What are the results telling us? For the scenario 1, we first look at the SNR versus the RSSI median values, where we find quite some differences for the antennas. If we think about it, it is not a surprise that we get a worse SNR with broadband antennas, because they pick up a lot of potential interferers in a broader frequency band. The magnetic antenna receives only a narrow frequency band. This gives us obviously a good SNR, however, it has a disadvantage in the RSSI. Moving to the transmitter 2 comparison, we find that for the short distance we have there, we always get a good SNR. Not a surprise. Looking at the variations, we find that obviously the magnetic antenna has a significant advantage with lower signal variations, which improves the probability for good reception. Interesting, isn't it? Scenario 2 is bringing us now closer to the range limits of our LoRa links. First of all, here is the proof that LoRa is able to work with a negative SNR. Second, we realize that not only the received signal strength limits the range, it could be also limited by the receiver's SNR. Of course, this depends a lot on the environment where we are in. In my home environment here, it seems that the limits from the RSSI and from the SSR would be roughly at the same time. However, we can estimate that if the noise level would be about 20 dB higher, we would then probably be limited by the SNR. Now back to the results. Again, the magnetic antenna has the best SNR and the least variation, but the worst RSSI. For the latter, I do not have a proper explanation other than that I used a longer cable and adapters from SMA to the N connector. I think I will try to develop the magnetic antenna a bit further, because I like the fact that it protects the receiver. It is practically a shortcut for electrostatic discharge or strong low-frequency signals. I also like the radiation characteristics that might be helpful in a case. Overall, we can say that the self-made quarter wavelength monopole has a slight advantage over the other antennas. We have seen that with 4 walls, trees and 60 meters distance we get close to the maximum range of our LoRa link. Of course, I must admit that we are working here with a very low transmit power and the standard spreading factor, which is giving us roughly a receiver sensitivity of -118 dBm. By increasing the transmit power and increasing the spreading factor, there would be a huge potential to increase also the range. My question is now, could we predict this? Yes, we can. Why? Because we are electronics unmasked. Let's try this with the parameters of scenario 2 on our spreadsheet tool. Our little wave propagation prediction tool here has some more features than we would need here. I will explain it in more detail in a later episode. We go straight to the free space propagation sheet. For our transmitter 1 prediction, we need to put in the 60 meters distance and of course the 866 MHz, which is our LoRa frequency, and the 0 dBm effective isotropic radiated power. Next, we need to insert the attenuation of our obstacles. The last sheet helps us with that. For 866 MHz we find a wall with 15 centimeters is -11.36 dB attenuation and a wall with 10 centimeters is -7.57 dB attenuation. Now we need to put the values to the spreadsheet. We need 3 times -11.36 and 1 time -7.57, and the trees we estimate with -3 dB. The predicted received power is -111.4 dBm, which is our predicted RSSI. From our measurement we got 109.5 dBm medium RSSI in this scenario. The accuracy of our prediction seems to be not bad, isn't it? Next we can try transmitter number 2 with 12 meters distance. The transmit power would be -10 dBm because the internal antenna has a bad performance. Then we have one wall with -11.36 dB and one window with -4.54 dB attenuation. The prediction result is -78.7 dBm versus 83 dBm from our measurements results. Still a reasonable prediction. Maybe in this case the window attenuation is a bit higher than the one that is given in the table. The nice thing about this tool is that you can adjust it according to your circumstances. Then you can extrapolate your predictions to other places wherever you want to operate any kind of wireless systems. This helps us a lot, first to dimension the system, and second to position the radio network elements to the right place. Another interesting question we could ask is, what would be the maximum range of our LoRa system in free space, or in case you put the receiver antenna outside the building? Let's calculate quickly the free space case. We just remove the obstacles from the equation and then let us increase the range on the top. We can predict here a decent radio link for a distance of 4 kilometers. We could get even much more range by increasing the transmit power to the allowed level of 14 dBm and a high gain antenna, for example 12 dB, that we could use on the receiver side. And with that we would reach more than 100 kilometers in free space conditions. There are reports that claim they could receive LoRa signals from weather balloons in a distance of 600 kilometers. Looking at the numbers here, this seems possible, even with the standard spreading factor. We will look into this a bit deeper in one of the coming episodes when we talk about our wave propagation prediction tool in more detail. The summary. Even with the very low transmit power of our LoRa boards, we get a respectable radio range. The maximum I could reach was more than 1 kilometer from the balcony of our house. In comparison, Wi-Fi has around 100 times more transmit power. However, it could not even make half the range in our scenarios. The LoRa radio range was always sufficient for my test scenarios in and around the house. Antennas can make a difference, even when the antenna sizes and gains are not much different. A self-made quarter-wave antenna is a good choice. The advantage over a commercial rubber-coated helix antenna is about 2 dBs, which is not significant. However, it could help in a critical case. In case we have strong noise from other bands, a magnetic antenna might be the right choice. Wave propagation prediction was demonstrated for our practical examples. We will come back to explain the tool in a later episode, because this can be helpful to plan your own projects. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.